You're welcome to stay as long as you can and dip out as soon
Yeah.
as you need to.
Yeah, we'll do. Thank you.
Okay. My best wishes.
Thank you.
All right. Let me start you off, like always, with the practice quiz. And go ahead and do problems 1 and 2. So number 2 is asking you to do number 1 in a different way, and it gives you a suggestion. So basically, try to do problem number 1 2 different ways. So let me give another minute. Problems 1 and 2, 2 different ways. All right, does anybody still need more time? All right, then let's look at problem number 1. All right, and one way to do it is to use rule 3 of logarithms. This one comes out front. So we could get log base 2 of 8, but that 5 will have come out front here. And then this is 5. Now this asks the question, what's the exponent you raise 2 to get 8? And you have to raise 2 to the 3rd power. And you get 15. All right, now, one of my questions is, how many of you did number 1 this way? Got the answer in that way. If you did that, put that into chat. If you didn't, you don't have to put anything into chat. How many of you wanted doing it that way? Okay, one of you. A couple. And, all right. Although that gets right to the answer, it doesn't give much insight into why this property of logarithm exists. If we do it again this way, I'm going to replace, as it suggests, that 8 with 2 to the 3rd. So it becomes 2 to the 3rd to the 5th. the exponents get stacked up on each other. And another way to look at it is 2 to the third raised to the 5th power. Okay, and power to a power, imagine 2 to the third if you're visualizing it out. It's 2 times 2 times 2, 3 times. Now that set of numbers, 2 times 2 times 2, gets written out 5 times. So there's 15 2's. So power to a power, we multiply. And we multiply the 3 and the 5 together. 3 times 5. Because of this multiplication that would happen in here. Oops. That's why you get this multiplication up here. Now 2 to what power is 2 to the 15th? 2 to the 15th is 2 to the 15th. And we get the same answer, but this starts to add some insight into why rule 3 is true. Is a logarithm is really an exponent. And an exponent to an exponent, we multiply them. And we start to see why this rule exists. Let's go to number 3. Do this run 2 different ways and state the property of logarithms involved, just like this one kind of added insight into property 3 of logarithms. This will add insight into a different property if you can do it 2 different ways. So let me give you a couple minutes here. Anybody need more time on this one? Alright, so let me do it one way. Of when I multiply and the base is the same, I just add the exponents. I don't have to put base 10 when it's base 10. I don't have to put this parentheses either. And then 10 to what power is 10 to the 8th is just 8. That's one way to do it. A second way to do it is I can use the property of logarithms that we had talked about as rule 1 yesterday. And that is when you make 2 logarithms out of 1 logarithm. multiplication sign changes to addition. And why does it change to addition? Because these exponents have that way of working. When the bases are the same, you just add the exponents. And so when you distribute the log, it has to become a plus. So 10 to what power is 10 to the third? That's 3. Similar thinking, we get 5 over here. And we wind up with the same answer of 8 over here. Alright. So, give me a little feedback. Did doing these two different ways add insight, or not really? Or is that good to review, or not all that helpful? Let me know. Let's go back to number 4. This is a classic quotient problem rule. But I want you to find the derivative of y prime without using the quotient rule. And I'll let you think about that, about how you can do this without using the quotient rule. You get a little bit creative and you're able to do it without the quotient rule. So again, don't use the quotient rule, but find its derivative somehow. All right, anybody need more time? So I can do this without the quotient rule. If I rewrite it as a product, two things multiplied together. But what's the power on this? It's got to be to the negative 1 power. Now, you don't need the quotient rule anymore. You can use the product rule from now on. We had to have the quotient rule before we learned the chain rule, though. Because to do this derivative, you're going to need the chain rule. So there was no choice. We had to teach you the quotient rule. But now that we know the chain rule, we don't need the quotient rule. We still use it plenty of times, but oftentimes we just avoid it. So it's the first. Hold it. I made the classic mistake. This is not y prime. That's y. Oh, let's keep my eraser here. So now let's go to y prime. Is the first, times the derivative of the second. But when you take the derivative of the second, you have to use the chain rule. Anything to the negative 1 is that times this to the negative 2 times the derivative of the internal plus the second function times the derivative of the first. And then we just clean this up a little tiny bit. And the 3 and the 4 become 12, negative 12x and we can put this thing in the denominator plus 3 times this one. All right. Hopefully that was clear. How to do a quotient rule problem, a division problem now without using the quotient rule. Now let's go to number 5. In general, y equals one function of x divided by another function of x, f of x over g of x. Find dy dx without using the quotient rule. So use the same kind of strategy we used in the one before it. And also, when you do this, you're going to get two different things. Get a common denominator between the two fractions and combine them together and simplify into one big fraction. So go ahead and do number 5. Anybody still need more time? So dy dx is equal to the bottom. Now that's if I use the quotient rule, but I'm not using the quotient rule. So let me start all over. I'm going to have to do y equals f of x times, now if I put a g and a minus 1 like this, that's bad notation, because when you have a function name and you put a minus 1, that's shortcut for an inverse function. We don't mean inverse function. So what I should do is make it clear. Like this. Okay, now dy dx. is first times the derivative of the second. Take the derivative of the second, we get this to the negative 2 power times the derivative of the internal function plus the second times the derivative of the first. Now I have two fractions. Let's take this first fraction and rewrite it negative f prime of x. No, there's no prime there. Negative f of x g prime of x over g of x squared plus f prime of x over g of x to the first. Now, these two fractions, I want to add them together. I want common denominators. So I'm going to say, well, geez, let me get rid of this first power because it kind of looks like a prime. Get kind of confused there. All right, so we're going to say times. We need another g of x on the bottom. So then we're going to be getting g of x squared. And let's rewrite this. And notice, we'll put this one first, and it's really bottom, times the derivative of the top, minus top, times the derivative of the bottom, all over the bottom squared. And now we see where the quotient rule came from. Do you recall that when I taught the section with the product rule and the quotient rule, we spent a fair amount of time visualizing why the product rule is the way it is. If I had 10 times 20 and I increased them both by 1, that was 11 times 21, it expanded both of the sides of the rectangle. And we saw that the quotient rule had some kind of intuitive appeal, but I never did anything like that. I mean, the product rule had intuitive appeal, but I never did anything like that with the quotient rule. And I told you, you're just going to have to memorize the quotient rule. I'll be able to explain why the quotient rule works only much later on in the course, and we had to have the chain rule to allow us to do this. And now we see why the quotient rule is the way it is. Up to this point, it was just a memorized rule that had no meaning behind it. All right. Let's go to number 6. Years since 2010, that's what X is. Y is the price of pine wood per square foot. So maybe you're in a furniture company and the price of wood is a huge thing you have to keep track of. Your whole business is going to depend on, if basic wood prices go up, sales go down, so you have to, start releasing people early in the year and all this kind of stuff. Vice versa, if the price of wood goes down, more people buy your furniture, and then you start hiring new people. And you got to make all these kind of plans for the new year based, and you're always watching the price of wood per square foot. So interpret with a complete sentence. Y prime of 10 is equal to 0.37. Let me give you a minute. And it should be a complete sentence that a third grader can understand. Reduce the math lingo as much as possible. Try not to use the word slope or anything like that. You can do that in an initial draft of it, but the final draft should be without that. Okay, let me have you go to your group, and everybody go ahead and input what they're getting so far with their group, and then kind of check in with the other folks. And then I'll call on a group in a minute for this. All right, group 6. Can you tell me what you wound up getting here?
So what we said was basically, in 2020, the price of pine wood is expected to increase 37% per square foot,
In 2020,
37 cents, something of that variant.
the price of pine wood is expected to increase by $0.37. I like that. I'm going to put one little clause at the end. What should that little clause be? Provided
Provided it maintains the, I guess, tangent line doesn't sound very third gradery.
That's
Stays
right.
on,
They won't understand this one. Provided,
provided it stays on task or track.
yeah. Provided we stay on the tangent line. They won't understand the clause at the end, but they'll understand the first part, and which is the main part, which is you did an excellent job. In 2020, price of wood is expected to increase by 37 cents if current trends keep prevailing, or there we're probably finally putting in a little technical terms, provided we stay on the tangent line. Okay. I want a little feedback on this. I think I've done enough of this. Perhaps I can stop reinforcing this. Maybe I still need to reinforce this, so let me know. Tell me, keep reinforcing this, interpretation of this, or hey, we got it, we don't need any more? Okay, I think we're kind of clear that occasional refreshers would be good. Alright, so from here, questions on homework. And my printer is doing a self-cleaning. That's the extra noise you're hearing. It's right next to my computer. Alright, we're going to go one at a time. Well, let's start with 26. So here on 26, where does the inverse exist? And use analytical graphical methods to determine the largest possible set of points on which the following functions have an inverse. Now, what does it mean that the largest set of points on which the following functions have an inverse? Another way to state this, what's the largest set of points on which, when you take the inverse, you'll get a function and it'll pass the vertical line test. And so we see this one right here on 26. It is a parabola. And a hint to complete the square, whether you complete the square or not, and there's different ways that you could figure out what the vertex is. Let me use their hint. X squared minus 2x. This idea of completing the square is, remember, if you take half of the coefficient, now this only works if the coefficient of x squared is 1. So if the coefficient of x squared is 1, you take half of the middle term, the coefficient of the middle term, so it's negative 1, squared is plus 1. That one see this plus 1 and minus 1, I insert it in there. They'll undo each other, but it'll cause this to become a perfect square. Now, we can see that the vertex of this parabola is 1, 7. Oops. So if we went 1 over 7 up, it would be an upward parabola like this. And so if you took the right half of the parabola or the left half of the parabola, you'd be fine. So the domain should be something like x greater than or equal to 1. That would work. Instead of completing the square, we could have also done the vertex formula for a parabola. Remember, negative b plus or minus square root of b squared minus 4ac all over 2a. That's a quadratic formula. If you get rid of the plus or minus square root part, you're left with negative b over 2a. That gives you the vertex of the parabola. And that's when x is equal to 1, that's the x-coordinate of the vertex. You plug in 1 into this formula here, and you'll get the y-coordinate of the vertex, which would be 7. And but you just want either the right half or the left half, so I'll take the right half. I could have taken the left half, and then that's all that we want. Kylie, does that answer your question?
Sort of. So it says, so if it wasn't like a parabola
Uh-huh.
and you're determining where it would have an inverse, I don't really understand exactly how to answer the question.
Okay, let me embellish a little bit more. This parabola is not a one-to-one function. Horizontal lines, horizontal lines are going to strike the graph in more than one point. Thus, if you reflect it across the line y equal x, you'd get a sideways parabola, which would not pass the vertical line test. Whenever there is any horizontal line reflected across the line y equals x, when you find its inverse function, will turn into a vertical line. And so it has to pass the horizontal line test for the inverse to pass the vertical line test. So we had to restrict, and we wound up saying, all right, we're only going to look at the right half of this function. And then we have a function that's one-to-one. It now passes the horizontal line test.
So
Yes.
if it wasn't a parabola, if it was, I'd say number 23, it's 1 over x minus 5. I know the vertical asymptote is going to be at 5. So does that mean that it's the range is from negative infinity to 5 and then 5 to infinity? Is that what you're stating as the largest possible sets of points that that function can be?
Okay. Let's look at number 23. So this one, you see there. And from the other side, it looks like this. All right. Now, number 23's graph is a one-to-one function. Any horizontal line only strikes the graph at most at one point. So the inverse is everywhere, except, of course, at 5. You can't have an inverse where the original function didn't exist at all. So the largest possible set on this one, the domain for 23, would be the same as the domain of the whole function, from negative infinity to 5 union 5 to infinity. It's this parabola part where it's not one-to-one, doesn't pass the horizontal line test. That's what we need, why we needed to restrict things for number 26.
So if you were to write that faster, so you're pretty much restricting the domain so it becomes a one-to-one function. So
Yes.
that number 23 would be the domain cannot equal, x cannot equal 5.
Correct. That would be the fastest way to write it. Domain x cannot equal 5.
Okay, so all you're doing is what is the domain and are there any restrictions that you need to do to find an inverse function, a one-to-one?
Correct. That's right.
Okay, thank you.
Make it
That
a
clarifies
one-to-one
it.
so that the inverse is also a function. That's right. All right, so that is 26. And then you had a question on 36. Let's pop over to that. And the instructions are to find the if inverse. Alright, so my first thing is I replace this with y. Then I interchange x and y. And then I solve for y. So I'm going to divide by 4. I'll put e to the 5y on the left. Now I need to solve for y. I got to get rid of this e. So I'm going to take the ln of both sides. Since the base is already e, so ln and e to a power are going to kill each other off. And I'm going to get 5y ln x over 4. And then I divide by 5. That's my inverse function. Does that clarify things? Any questions on 36? All right. We had 38 and then 61. Let's go to 38. All right. So, same instructions. Interchange x and y. And now I need to solve for y. So I'm going to, for this one, I'm going to put a giant 10 as the base. This and this, the inverse, they kill each other out. I get this. So y is equal to 1/4 times 10 to the x. There, my last step, probably a good idea to do this, replace y with f inverse of x. And then I have that. Any questions on 38? Alright, and then 61. Here it is. 100 grams of a particular radioactive substance decays according to the formula, where T measures time in years. When does the mass reach a level of 50 grams? So whenever I have something like this, I always write out what the input variable represents. T is time in years. And M, what does that represent? This is the mass.
Does it equal mass?
Yeah. In grams. So, when does the mass reach a level of 15 grams is really asking, what is T? When M is equal to 50. So we've translated that into words, and now we just need to plug in the equation. 50 for the M. Over this. Divide both sides by 100. So e to the negative t over 650 is going to equal 50 over 100 is 0.5. And then I'm going to, I have to get rid of that e. So I'm going to take the ln, use those inverse functions. These are going to kill each other off. So now I get so then I multiply both sides by negative 650. This is what I'm going to call my exact solution, and then I'm going to punch this out into my calculator. And I get 450.54. years. So it takes about that much time for that to happen.
So I guess I knew how to do this, but I got confused when it said M of T.
Ah, okay. That notation can be confusing. And I like the way you said it, M of T. So it's just saying that M is a function of T. Sometimes we put the output letter, and then we put parentheses the input letter to show that M is a function of T. It doesn't mean M times T or anything like that, but I can see how that can be confusing. All right, everybody clear? Any other questions?
Gerardo had a question for number 59.
59. All right. Okay. So to solve this problem, it's difficult because the x in a really bad position. It's up in the exponent. What's the best way to bring it down from the exponent position? Use rule 3 of logarithms. But there's no logs in this equation. Can we insert logs? Yes, we can, because you can do anything to both sides as long as you do the same thing to both sides of the equation. So I'm going to do ln of both sides. ln of 3 to the 3x minus 4 equals ln of 15. And then this gets to come out in front. Divide by ln 3. So let me come back here. And I get 3x minus 4 is ln 15 over ln 3. Move the 4 to the other side. 3x ln 15 over plus 4 divide by 3. X is equal to ln 15. Both parts have to be divided by 3, both terms. Divided by 3 ln 3 plus 4 thirds. And that would be my exact solution, and then I'd also punch this out in my calculator like I did over here and get an approximate solution as well. And label both exact solution and approximate solution. Any questions on 59? Alright, and is that it for questions?
I just had a theoretical question. So if you have a number with an exponent of an exponent,
Yes.
how would you figure that out?
Alright, we're going to have to deal with those. The textbook calls them tower functions, and they're very unusual functions. Let me just show you. If I have y equals x to a constant, we call this a polynomial function. If I reverse the roles, if the base is a constant and the exponent is up in the variable's up in the exponent position, this is called an exponential function. But if I have a variable in both places, let's say x to the 3x minus 1, this is not a polynomial function. It's not an exponential function. It's way more powerful. It grows way faster than either one of these does. And some textbooks just never refer to this by name, and it's just because it's a very unusual way hard. But this textbook calls it a tower function. And the rules, the shortcut rules for polynomials don't work on it, because the exponent has to be a constant. The shortcut rule for exponential functions don't work on this either, because the base has to be a constant. So neither of these work if you have a tower function. And we always use the same trick when we meet tower functions. We take the ln of both sides. You could use any base you want, but we tend to prefer ln. So we take the ln of both sides. So this is what we'll get used to whenever we see this. Now why do we do that? So that this can come out in front. And then we can deal with it. And that's the only way we know how to deal with these tower functions, is take the log of both sides and then bring the exponent down. And then we can have a handle of working on it.
So are there problems where there's a tower function on top of another tower function?
If that was the case, you might have to take the ln of both sides more than once. But that's really the tool that we use every time, is taking the log of both sides. Yep, you could have tower on tower, and we'd handle it the same way. Good question. All right, let's do the very beginning of this new section. .9 derivatives of logarithmic and exponential functions. And this is what we were setting up for by reviewing exponential and log functions. And this section has 4 important formulas. And you know, when you go to education school, so I went to, I was first a high school teacher. I only lasted 1 year. I didn't like teaching in a high school. It seemed to make a really big difference if students chose to be there or not. I didn't like teaching where students didn't have a choice about being there. And but when I was becoming certified as a teacher for high school, I had to take education classes, and one of the things they taught was, you know, you should have your objectives. You should be really clear about what you want students to understand when they get done with a section. And so I have these kind of mentally every time figured out, but often I don't write these down. But in this section, I realize it's very important that we have these listed. And if you're taking notes, that you write these down in your notes, because we're going to get to a bunch of different things in this section today, and you might realize at the end, like, oh wow, what was I supposed to get out of that? Well, this is what you're supposed to get out of it, because there's so many different things. There's 4 different things. You're supposed to be able to understand and be able to use. And remember, you're going to have to memorize these. These 4 formulas. And the memorization of these will come a lot easier once you understand them. So we'll work on having you understand these 4 rules. And it is time for a break. So we'll start again in a little while, but before you take the break, you might want to put these into your notes. .43 p.m. All right, we will start again. And 3.9, derivatives of logarithmic and exponential functions. So notice the first rule is something that we already know. The derivative of e to the x is e to the x. And I'm not going to spend any more time with that except to realize how this might have been first observed. Remember, we had done a derivative of e to the x is e to the x. Yeah.
Professor,
Yes.
are you writing on your whiteboard?
Oh, I am, and thank you. The derivative. Thanks for catching me there, Kylie. I could have gone on for a while. When we had thought of what's a function whose derivative of itself is itself, that would have to be a function whose heights and steepness exactly match. The height of the function is its steepness. So when the function is at a height of 1, its steepness is slope of 1. And the exponential function does that, has a slope of 1 right there. By the time you get up to a height of 2, you got to have a steepness of 2. Your instantaneous slope would be 2. By the time you get to a height of 3, your slope has got to be 3. It's a very fast growing function. It's the exponential function. It has that property. The heights height of y equals e to the x is always equal to its slope. So at any point on this curve, you look at its height is 3, its slope is 3. Any point on this curve, its height is 2, its slope is 2. Now this one, its height is 1/2, its slope is 1/2. Slight height is 1/4, its slope is rise 1, runs 4, 1/4. Always the heights and the slopes are equal. That's a really unusual property, and it happens only with exponential functions. And Alright, now I want to take a side route for a moment, generalizing a derivative rule. For chain rule use. Suppose that we look at the power rule. The power rule says the derivative of x to the n is n x to the n minus 1. If we generalize this rule for chain rule usage, it becomes how we really use it. You don't have to just use it on x to the n. It could be any function of x to the n. We'll call it u to the n. Where u is some function of n. Kind of like we did when we were doing the alternate version of the chain rule. U could be the inner function. Okay. Then the derivative is n u to the n minus 1, but then we have to chain on du dx. Right. So, before we're done today, we're going to be taking all 4 of those rules that I listed in the objectives, and we'll be generalizing them for use of the chain rule. And so the final version of those objective rules will look a little bit different. They'll look like this more, with u's instead of just x's. They'll have u's and x's. So, and that's how we actually use them most of the time. All right, now let's go to, let me take a snapshot here. Put this in. Let's come back and ask an important question. When we take the derivative of exponential functions, very often the base won't be e, and we'll still need to take its derivative. So the derivative of e to the x is e to the x. That's great. And the derivative, if it was more complicated, if the upper function was a function of x, e to the u, we're still okay with that, because we would just get e to the u again times du dx. Chain rule. But what if the base is not e? All of our theorems so far require the base to be e. And the thing is we don't need to adjust these theorems. We can just force any base to be e. And when you force the base to be e, everything will work out right. And when you do that, we will wind up coming up with a theorem that'll look like this. The derivative of a to the x, and where a doesn't necessarily have to be e. A could be e, could be something else, could be like 2 or 3. We'd never use a being negative. Remember, exponential functions always have positive bases. All right. It'll turn out, it'll look very similar to this, except we're going to tag on what we'll call a penalty factor. The penalty factor will be the penalty for not having the right base. Since it didn't have a base of e, the penalty factor will be lna that tags on at the end. Okay. And now theorem means something that has been proven to be true. Let's ask the question, why is this true? Why does this theorem make sense? And we're going to demonstrate with d dx of a very specific one. Instead of any number a to the x, it'll be 2 to the x. The derivative of 2 to the x. All right. Now, we're going to say that that's the same as the derivative of, and I'm going to rewrite 2 to the x as e to some power. Now, remember this was in the practice quiz yesterday when I said rewrite something with a different base. So 2 to the x can be rewritten as e to the what power up here. So let me give you a moment. Go into your groups, see if you can remember what that was, chat about it for a little bit, and then I'm going to ask a group. How did we do this? It was in the practice quiz yesterday. It means the same thing as 2 to the x, but it has a base of e. I'll give you a minute. All right, group 3. What do you have?
Um, we don't really know. We're thinking e to the 2x.
E to the 2 to the x, like this?
No, e to the 2x.
Just
Oh,
plain old 2x, like this?
I don't know. I'm just guessing here.
Okay, that's a good guess, because we got to get the ball rolling somehow. So we got to take a guess to get going. All right, you're on the right track using 2 and x. But we need something that'll cancel out with this e, because there's no e in here. What will cancel with e? What, when you combine it with e, kind of undoes it?
Ellen.
ln. And then we put exactly the same thing up here. So notice e and ln kill each other off, and it's the same thing as that right here. All right, now this is going to be the derivative. I'm going to write it down here though, d dx of e. There's something I can do with this. So that it's not 3 layers high. There's this one, then you go up 1 layer, and then you go up 1 layer again. 3 layers deep of exponents. There's something I can do with that thing in the black box. And it's what rule? Rule 3. Rule 3 says this gets to come out here. All right, now what we've done is we started out with something whose base was not e. And then we just said, well, let's just make the base e, because it's possible to do that. And then we did one of the rules, rule 3, to make it look kind of ordinary now. How do you take the derivative of e to the u? You take that derivative by, the derivative of e to the u is e to the u. times the derivative of the u. Now, this derivative, well, ln2 is just a constant like the number 5. And the derivative of 5x would be just 5, so the derivative of this is just ln2. Now, this is going to give me e to the x ln2 times ln2. Now, look at this theorem. According to this theorem, the derivative of, if you replace a with 2, derivative of 2 to the x should wind up giving me 2 to the x ln2. Well, I am getting the ln2 to show up at the end. But this thing right here isn't supposed to be this complicated thing. It's supposed to be just 2 to the x. There's something I can do with this. How do I get this to simplify? If the e and the ln were right next to each other, they cancel each other out. But only if they're right next to each other. Because this x is in between the e and the ln, they don't cancel each other out. So is there any way to move that x so it's not in between them?
Can you
Yes,
do the same rule as you did?
that's right. Rule 3 again, but using it in the other direction. So this is going to be e to the ln, 2 to the x, ln2. And then e and ln, now they kill each other off. And I get 2 to the x ln2, and this rule is starting to make sense. All this rule is a shortcut, so you don't have to force it into base e every time. If you force it into base e every time, you'll do this kind of thing, but you'll wind up getting this result. So this is just a shortcut to get to that result right away. And this theorem allows us to do problems like this and get them instantly. Y is equal to 5 to the x. dy dx is equal to, well, according to this theorem, it's a to the x. The derivative is still a to the x. And then I have the penalty factor, ln of whatever the base was, is my penalty factor, because it's supposed to have a base of e. If it doesn't have a base of e, it has this penalty factor tagged on at the end. All right? Just to get comfortable with this, let me ask you to do this one. 3 times 7 to the x. Figure out what y prime is. Okay, I'm going to give you 30 seconds more. So this is 3. The derivative, just so that just the derivative of constant times a function, the constant just stays out front. Derivative of this is derivative of a to the x is a to the x, and then ln of a. Now you might tend to think, oh, we should have put our answer in this format. Put all the constants up front. And you could write it like this, except people will get confused and they'll think, ooh, is it the ln of 7 times 7 to the x, or is it just the ln 7? Or you'd really have to put this in parentheses to make it clear. So just to make it so that we don't have to use parentheses, we use a convention that we put the ln way at the back. So we leave our answer like this. All right, let's do one more. 3 y equals 4 to the 3x squared minus 7. Figure out what y prime is. Okay, so this is this right here, but it's now A, and it's the same theorem, but remember we talked about generalizing. Any of these theorems can be generalized where this x could be replaced with u, and then you'd have an extra du dx at the back end. So this, the derivative of e to the u is e to the u, penalty factor for having the wrong base, and then you have to tack on the derivative of the inner function, the u, and that's going to be 6x. So if I rewrote this, I'd probably put it like this. And I'd save my ln4, although it's a constant, I'd put it way in the back, so I don't have to put parentheses around it. Alright, give me a little feedback. Is all this clear so far, or is it getting fuzzy on like number 3 or anything like that? Just let me know where you're at with all this.
Would I be able to would I be able to ask you've got 6x?
Yes, that's a 6x. And what was your question about the 6x?
How you got that?
Oh, how did I get that? All right.
Yes.
It's the derivative. It's this part right up here. Du dx. This came from that. So when it's not e to the u, when it's not the derivative e to the u, so d dx of this, the x and this are not exactly the same. This is a function of x, so we have to tag along the derivative of that at the end. And I hear that it's not easy for everybody to learn online. Some of us have distractions like a million kids all around us, and that would make life a little bit more difficult for doing this kind of learning. Good job of continuing to learn no matter what the obstacles are. I remember when my kids were young, it would have been really hard to learn at home with them. I used to have to stay late in my office in the evening because it was just so hard to get home and get anything done. All right. So we started out with this rule. And then we moved to this rule. D dx of a to the x is a to the x ln a. And of course, each of these can be generalized for a more complicated thing like a u up there. Okay. And now we're going to go to our third case now, which is a theorem. If you take the derivative of the natural log of x. Now, before I do this, let's review what the natural log is. Natural log of x is the same as log base e of x. And what's e? Does anybody remember the approximate size of e?
2.71.
2.71, 828 if you wanted to keep going. It's the second most popular irrational number after pi. And so a lot of people have memorized a lot of digits of this, just the same thing as with pi. All right? Now, where does e come from? E comes from, it's more complicated than pi, where pi is just any circle. You can take any size circle and measure the distance around it to the distance across it and divide those two things. The distance around it divided by the distance across, you always get pi every time. E is much more complex. E, definition of E, is the limit as n approaches infinity, 1 plus 1 over n to the nth power. Now we know about limits, so we can kind of get a feel for this. Let me make a little table. N and 1 plus 1 over n to the nth power. If n is equal to 1, then what will 1 plus 1 over n to the nth be? Anybody tell me?
Just one? Oh,
Close.
yeah.
Really close.
That's 2.
2. Because you're going to get 1 plus 1, which is 2, to the first, which is 2. And now if you put in 0.1, hold it, 10, let's make it 10 times as big every time. If n is 10, the slow way to write this is 1 plus 1/10 to the 10th power. But the fast way to write it is it's going to be 1 plus 1/10 is 0.1. So it's 1.1 to the 10th. And then if you pull out your calculator, you can quickly do this. 1.1 to the 10th power. And I'm going to get 2.5937, so on. If I do 100. Fast way to compute this, 1.01. Notice the base is getting smaller while the exponent is getting bigger. They kind of have a neutralizing effect, but it's not totally neutral. It's going to make this thing get bigger. 1.01 raised to the 100th. And notice I'm getting closer to this. And if I did my E with more digits, 2.7182818828, it gets into no repeating pattern. Quickly gets out of that 828 stuff. Because being an irrational number, that can never be a repeating pattern. We see that the bigger this gets, the closer this is going to get to this. Let me do it one more time. See how we're getting pretty close to this. And as this goes towards infinity, this goes towards E. So the limit is that. And this might seem like, this is a really strange way to get this so important of a number. And whoever came up with this crazy thing? Well, actually, it comes up naturally if you were doing compound interest. And, if I had a full day to devote to this, I could have you go through compound interest and show you that if you take $1 and you get 100% interest, compounded one time a year, you'll get $2 at the end of the year. But if you have $1 at 100% interest, compounded twice a year, you'll get a little bit more than $2. You'll be getting kind of around, $2.60 maybe, something like this. If you had $1, 100% interest, compounded 4 times a year, then 12 times a year, monthly, and then 365 times a year, daily, and you keep increasing how many times you're compounding it per year. And you're only doing it for 1 year, though. The greater the number of compoundings, the closer you're going to get the answer to E. It comes as a natural result of exponential functions with compound interest. All right. So let's come back to this theorem. The derivative of ln x. Now, the derivative of e to the x was e to the x. The natural log function is the inverse of e to the x. So I would kind of expect, well, maybe the derivative of ln x is just ln x or something, but it doesn't turn out to be that way. It turns out the derivative of ln x is 1 over x. And let's talk about an implication of what this means and kind of get an intuition about this. Let me copy this in first. Oops. All right. So we have now, think of this as the slopes of y equal ln x are the same as the reciprocal of x, 1 over x. And let me draw a picture. If I take y equals ln x, and I was to graph that, well, before I graph it, let me graph y equals e to the x. Y equals e to the x. We talked about this yesterday. goes through a height of 1 and increases very fast because e to the 0 is 1. And so this goes up even faster than y equals 2 to the x. It doesn't go up quite as fast as y equals 3 to the x because e is 2.71 approximately. Now, that's e to the x. The natural log is the inverse function. The inverse of any function is a reflection of this across the line y equals x. So this point right here would reflect, go directly perpendicular to the dotted line, the same distance over, it becomes this image point over here. And you wind up getting this curve here. This is y equal ln x. Now, on this function, y equals e to the x, if you put in a large point like 10, so all you have to do is go over 10. The height is going to be e to the 10th power, which is huge. Let me just punch that out of my calculator real quick. Which is already 22,026. So if you go just over 10, you have to go up over 22,000 over there. Now, on this function, y equals ln x, I told you you can get any, whenever you have the inverse function, it's the same as just flipping these values around. So e to the 10th would go over here. And then you'd get the ln of e to the 10th. ln of e to the 10th asks you, what is the exponent you put on e to get a result of e to the 10th? Well, you just put a 10 on that. So this function, you have to go, if you want to get just to a height of 10, which is not very high, you have to go out more than 22,000 in that direction just to get up to a height of 10. As fast as this is growing, that's as slow as this is growing. Now, we're going to look at this theorem in relation to this blue curve. This says that the derivatives of this, or the slopes of this, are always equal to 1 divided by the x-coordinate. So if I'm right here, what's the x-coordinate of this? This is 1. So this point, its x-coordinate is 1. The slope should be 1 divided by 1, which is 1, which it is. Let's go out, let's say we're at 3. So we go to this point. The x-coordinate of that point was 3. The slope is going to be 1 divided by 3, which that is, it goes up 1 over 3, it's not very steep. But the more you go to the right, the less steep the slope is. So if you go all the way to 10, you're going to go up 1/10. And so on. So now, also it's got to work in reverse. If you went to 1/5, way over here for your x value. Then you're way down here. Now the slope is the reciprocal of 1/5, but the reciprocal of 1/5 is 5. And that's what we're getting. Very steep slopes to the left of 1, very shallow slopes to the right of 1. All right, so the derivative of ln x is 1 over x. That's kind of a graphical meaning of that statement. All right, now, when we generalize this, for the use of the chain rule, d dx of ln u is 1 over u times du dx. Right here. So this is actually what we would use more often. This is for the very simple problems. This is the rule we use for the more complex versions. So print out the screen. So the only rule of those two that you really need to know is the more complicated one. d dx of ln u is 1 over u du dx. And let me give you a couple problems to get comfortable with this rule. Y equals 6 ln x, find y prime. I'm going to give you 30 seconds for this. All right, this one, the derivative is 6 times the derivative of ln x, but the derivative of ln x is 1 over x. So y prime is just 6 over x. Now, let's look at this problem if we made this slight modification. Instead of the 6 being out front, the 6 is inside. Find y prime. Seems like a minor change, but it makes a major difference in the answer. All right, I want you to go in your groups, check with each other on what you're getting with this. And I'll call on a group in a minute. Okay, anybody need more time? All right, group 4, what are you getting for this?
1 over 6x.
It feels like 1 over 6x, but there's something wrong with that. The u in this case is 6x. So you're kind of using this rule right over here. The derivative of ln u is 1 over u. But you have to put this part, du dx. But what's the derivative of 6x with respect to x? It's just 6. And what's going to happen with these two 6's? They're going to cancel each other out. Now the first time I did something like this, I thought, oh, I must have made a mistake. This can't be the right answer, because if this was just ln of x, my answer would have been the derivative is 1 over x. But this is the ln of 6x. How can the answer still be 1 over x? But this is the case. The answer is 1 over x. And let me add some insight into this, because it doesn't feel right. The 6 should somehow affect the answer. All right, let's do this a whole different way. I'm going to go like this. How many times did I write down ln? Just once. Suppose I wanted to write down the ln twice. What sign goes in between these?
Addition.
Addition. So now when I take the derivative, what happens? What is the derivative of ln 6? It's just a constant, so it's 0. Plus, and then this is 1 over x. It starts to make a little more sense. The ln of 6x, the graph of that is the same as the graph of this. It's just got a horizontal shift. Not a horizontal, vertical shift. It's just been shifted up a little bit. And so when you look at the slopes are the same as the slope of this. So it's just 1 over x. Number 3, if you took ln of 13x, y prime is still going to be 1 over u times du dx. The du dx will be the 13. The 13s will cancel. No matter what constant you have out in front, it'll just disappear. And this is one of the crazy things it takes some getting used to with the ln function. It just it won't seem right at first. And we have another significant idea, which is so another theorem. Let me print this screen first. It's getting hot in my little office over here at home. I think we're headed for I said kind of quite a heat wave. I was talking with my mother up in Michigan. She said the same thing is happening up there. Big heat waves coming, so I guess it's across the country. All right, there's another theorem. The derivative of, now what we just did was ln x. But what if the base isn't e? Then we put log base a of x. Now if you take the derivative of ln x, you just get 1 over x. we're going to get something very similar. 1 over x. But remember the penalty factor for exponential functions when the base wasn't a. We got ln a tagging along. Here we're going to get the penalty factor, and it appears in the denominator. Now, it's not easy. I mean, it's very easy to remember this. At first, when I was first learning this, I was like, oh, how am I going to remember to put this in the denominator? Might I put it up here? And then I finally realized, if there is a denominator, that's where the penalty factor goes. The other one didn't have a denominator. So, when you take the derivative, if there's a denominator, the penalty factor goes in the denominator. And let's do some example problems to get used to this. Number 1. Y equals log base 5 of x. Find y prime. Let me give you 30 seconds for this. Right here, it's exactly this rule. It's just the 5 is replacing the a. So I'm going to get 1 over x and then ln 5. So how I look at this though is that if this had been log base e of x, then I would have 1 over x. That would be it. But since the base wasn't e, I have the penalty factor, which is right here. Okay. Now let me review that in the context of exponential functions. Y equal 5 to the x. Y prime is, what's that again? It's the same thing, and then penalty factor, because the base wasn't e. Notice there was no denominator here, so this penalty factor didn't have a chance to go in the denominator. When there is a denominator, the penalty factor goes in the denominator. All right, and let me also compare this one to e to the x. Suppose you took the derivative and you got e to the x, and you imposed the penalty factor even when you weren't supposed to. It would be asking ln of e. The unwritten base is e, so it asks e to what power gives the result of e, and so this whole thing is 1. And then the end result is just e to the x. So this, if you impose the penalty factor when you didn't have to, it doesn't hurt. You'll still get the same answer. So that's one of the reasons why you don't really have to memorize 2 rules, just this rule. You don't also have to memorize the d dx of ln x is 1 over x. This rule incorporates that, because if you use this rule when you didn't have to, suppose it was base e, you just get an extra ln e, which is times 1, which keeps the answer the same. Over here. Alright, so let's do another one. Suppose y is equal to log base 7 of 3x squared minus 2x plus 1. Find y prime. Anybody need more time? So this is this, but we're thinking of this as a u now instead of an x. Since that's a u, they're also going to have a du dx. So I'm going to have 1 over u and then I'm going to have a penalty factor for not having the right base. And then I'm going to have this derivative, du dx, tacked on. And this becomes 6x minus 2. And so my final answer would be y prime is equal to 6x minus 2 over all this stuff. Any questions? So we've had a lot today. We had 4 different rules that you're going to wind up having to understand and commit to memory. And let me give you 1 minute on your own. See if you can, without looking back at your notes, try to remember what are the 4 different rules. I'll give you a minute. Okay, so my summary. If the base is e, d dx, e to the x is e to the x. And d dx of ln of x, that has an implied base of e, is 1 over x. If the base is not e, then the rule changes. d dx of a to the x is a to the x penalty factor ln a. I think of that as the penalty factor. It was supposed to have a base of e, it didn't, so we got to tag that on. And then d dx of this one when the base isn't e. To write it when the base isn't e, you have to put log base a of x is 1 over x ln a. Now, there are 4 rules. But actually, if you just remember these 2 rules, you have these 2. Because remember, if you use this rule and you put the penalty factor when you didn't have to, because the base was already e, it just multiplies by 1. And so, if all you commit to memory is these 2, you're totally fine. Now, generalized forms. this is how you actually tend to use them. And this one becomes d dx of e to the u. Is e to the u du dx. This one becomes d dx of ln u is 1 over u du dx. These d dx of a to the u is a to the u ln a, penalty factor, times du dx. This one is d dx log base a of u is equal to 1 over u penalty factor ln a du dx. Now, for all of these rules, if you just memorize those two, you have it all. This still works if the base was e instead of a. This still works if this was an x instead of a u. You just get dx dx, which would be 1. Anything multiplied by 1 is itself. Just memorizing those two rules really summarizes everything we did today. So, your homework is 3.9. And there's stuff due for final form at midnight tonight. And double check that real quick. 3.5, 3.7, and 3.8. Final form of those. And it says on our schedule sometimes worksheets, and those are really kind of notes for the instructor to use these worksheets, so you don't have to worry about that. And any questions or comments?
I do have one question.
Yes.
I'm gonna use the first rule. On the right side, when you put equals e the u power
Uh-huh.
and it's times the derivative of u,
Yep.
that what it means when you put du divided by dx.
Yep.
Alright.
It does mean take the derivative of that internal function. So an example of this would be derivative of e to the 5x cubed plus 4. That's equal to e to that thing again, but times the derivative 5x cubed plus 4. That would give you that. That would be it. Does that answer your question?
Yes.
Okay. Anything else? All right, we'll stop here, and you all have a great weekend. I will stop the videotape.
Hey, Robert.